8152. Which of the following is the ultimate limiting factor of turbine engine operation? A. Compressor inlet air temperature. B. Turbine inlet temperature. C. Burner-kin pressure. The correct answer is B. The turbine inlet temperature is the ultimate limiting factor of turbine engine operation. It refers to the maximum temperature that the gases entering the turbine can reach without causing damage to the turbine blades. This temperature is typically limited by the materials used in the turbine blades, as they have a maximum temperature limit that cannot be exceeded without risk of structural failure. 8153. The recurrent ingestion of dust or other fine airborne particulates into a turbine engine can result in A. Foreign object damage to the compressor section. B. The need for less frequent abrasive grit cleaning of the engine. C. Erosion damage to the compressor and turbine sections. The correct answer is C. The recurrent ingestion of dust or other fine airborne particulates into a turbine engine can result in erosion damage to the compressor and turbine sections. When these particles enter the engine, they can accelerate and impact the compressor and turbine blades at high velocities. Over time, this continuous impact can cause erosion, wearing away the material and reducing the efficiency and performance of the engine. 8154. Which of the following engine variables is the most critical during turbine engine operation? A. Compressor inlet air temperature. B. Compressor RPM. C. Turbine inlet temperature. The correct answer is C. While compressor inlet air temperature and compressor RPM are also important parameters, they do not have the same level of criticality as turbine inlet temperature. Compressor inlet air temperature affects the air density entering the engine, which can impact engine performance, but it does not have the same potential for immediate damage as exceeding the turbine inlet temperature limit. Compressor RPM is an important parameter for controlling the airflow and compressor performance, but does not directly impact the temperature limits of the turbine section. 8155. Reduced blade vibration and improved airflow characteristic brought about by A. Fir tree blade attachment. B. Impulse-type blades. C. Shrouded turbine rotor blades. The correct answer is C. A shroud is a protective covering that surrounds the outer edges of the turbine rotor blades. It creates a barrier between adjacent blades and helps to contain the airflow within the turbine section. This shroud design offers several benefits. Reduced blade vibration. The shroud provides structural support to the blades, reducing their susceptibility to vibration and potential damage. It helps to dampen the effects of aerodynamic forces, such as flutter or resonance, which can lead to increased blade vibration. Improved airflow control. The shroud helps to guide and direct the airflow more effectively through the turbine section. It reduces the leakage of gases between adjacent blades, improving the overall efficiency and performance of the turbine. Enhanced aerodynamic efficiency. By minimizing airflow losses and improving the flow characteristics, shrouded turbine rotor blades can enhance the aerodynamic efficiency of the turbine. This can lead to improved power output and fuel efficiency. 8156. Which turbine engine compressor offers the greatest advantages for both starting flexibility and improved high-altitude performance? A. Dual-stage centrifugal flow. B. Split-spool axial flow. C. Single-spool axial flow. The correct answer is B. The split-spool axial flow compressor offers the greatest advantages for both starting flexibility and improved high-altitude performance among the given options. Here's why. Starting flexibility. The split-spool configuration allows for independent rotation of the low-pressure compressor, LP, and high-pressure compressor, HP, spools. This design enables better starting flexibility as the LP spool can be accelerated independently to provide sufficient airflow during engine startup. It allows for a more controlled and efficient engine start, especially in challenging conditions such as low temperatures or high altitudes. Improved high-altitude performance. The split-spool axial-flow compressor is particularly beneficial for high-altitude performance. By having independent rotation of the LP and HP spools, the compressor can maintain a more optimal compression ratio throughout a wide range of altitudes. This helps to maintain higher engine efficiency and power output at high altitudes where the air density is lower. The ability to adjust and optimize the compressor stages independently allows for improved performance and better matching of the engine's airflow and pressure requirements.